Hi everybody. No, I didn't pick my nose. I was just wiping the side of my nose. Hi, how we doing? Yeah, so as you see in front of you, we're going to be getting into something called differentials. Okay, and differentials are basically using tangent lines to approximate values of functions on a curve. So why not just jump right into it, look at an example of what I'm talking about, and then we'll talk about how it can tie into some really neat applications in the quote unquote the real world. So if you look at the problem that I have up here, it says find the equation of the tangent line t to the graph of f at the indicated point and use this linear approximation to complete the table. So if you look at the function, where's my little pen here? Here we go. Oops, I'm moving that. I didn't mean to. Okay, so if you look at the function that we're talking about is clearly a parabola, and all the interesting stuff is going on in the neighborhood of 2 comma 4 for us, okay? In the meantime, I'm going to show you something real quick. I don't know if I could do this. I want to show you what it looks like outside. And yeah, it's really coming down, isn't it? Can you see it out there? Yeah, that's my neighbor's yard. Those are some pretty old and sweet people. But anyway, hi, I'm back. Just a quick little, yeah, I'm sure. I don't know how many of you are up. I'm sure some of you are on your Google Doc. Where's the stuff we're supposed to do? It's coming, okay? It takes a while to upload and do all this other exciting stuff. So in any event, we have this function, we have this parabolic function, and we are in the neighborhood of the whole 2 comma 4. And if you look in the table, f of x is our function, x squared, and then t of x is actually our tangent line. So we want to use the tangent line when we graph it to basically say compare the values on the function itself versus the values on the tangent line, just to see how close and how good the tangent line approximation is to the actual value. And the nice thing is that anytime you can pause, go back and say, what did she just say? Because sometimes I know some of you dimwits aren't paying any attention. So anyway, so if I were to look at it, just to give you a visual, I put it on the calculator just for now. And if you look at this right over here, this is the point 2 comma 4, okay? Right over here. And if you noticed on our table, we have 1.9, 1.99, 2, 2.01, and 2.1. If you look at the values for x here, you'll notice that they are very close to 2. So they're like basically, if I go back into my calculator over here, they're talking about the values around the neighborhood of 2 because the 0.24 is right over here. So anything, and this is 3, and then over here is 1. So if I say between 2, 1.99 and 2, we're literally talking about, let me see if I can get a little color here. We're talking about from here actually to there, okay? So it's actually smaller. It's from here to here. And if you look at it, the tangent line and the function look really close together. So what we're actually going to do is we're actually going to calculate those values and see where it goes, okay? So let's go back to this. And what I need you guys to do right now is to find the equation of the tangent line for this function at the 0.24, and I will meet you back here. Okay, so as we pause here, you should have gone ahead and noted that your tangent line should be y minus 4 equals 4 times the quantity x minus 2. If you actually solve for y, you get y equals that plus 4 because you just add 4 to both sides. So that's essentially your tangent line. So hence this is your t of x right here. So what I need you to do now is I need you to go ahead and substitute in those values. So what you're going to do is going to find out what f of 1.9 is. So you're going to do 1.9 squared, then you're going to do 1.99 squared, 2, and so forth. And then for your tangent line, you're going to take those same values. So you're going to put 1.9 in for x and solve for whatever y is, and then correspondingly go there. I'm going to do it simultaneously, and I will fill out the tables, and I will meet you back. All right, so I am back, and if you look at this, you will notice that you should compare your values in your tables versus mine. Now, what's really interesting is that if you were to look at these values, whoops, let me go back to my pen here, because if I don't, come on, why are we acting behave? Come on, all right. If you look over here on the parabolic function, on the parabola, the y value when x is 1.9 is 3.61, and the tangent line is 3.6. So the only difference is 1/100 of a point. So it's like, it's pretty darn tootin' good, and that's at 1.9. If we get closer and we do 1.99, you have your y value on the function is 3.9601, and your tangent line is 3.96. So you're talking like 0.0001. You're like 1 over 10 thousandths off. That's pretty darn tootin' amazing. And then clearly the tangent line and the function are always going to share the same y value at the point of tangency. But if you move over here and you're making these observations, clearly the tangent line is a phenomenal approximation when you're tight in the neighborhood for f. Because if we said, for example, if I use the same tangent line and I'm like, okay, well, let's calculate the value when x is 4, right? Well, the thing is that if I go in here to my graph over here, if I go over here to 4, like 4 is up here on the function, right? Look over here, this is where 4 is on the function, and then the y value on the tangent line is all the way down here. So this right here, this space between the two functions, between the tangent line and the original function itself, there's a big space there. But if you hang out in the neighborhood of the point of tangency and you use that tangent line at that point, all the points in his neighborhood are going to be complete and total rock stars. So the further away you get from the point of tangency, clearly the less good your tangent approximation will be. Now the cool thing is if you wanted to go and see, use a tangent line to approximate the value of the function at 4, what you want to do then is find the equation of the tangent line at x equals 4 and play in that neighborhood. So why don't we do that, okay? So what I'm going to do is I'm going to hit pause, and what I want you to do is find the equation of the tangent line at x equals 4, and I'll meet you back here. Okay, so what I did was I took the time to sketch the function and plot the point well, why isn't my pen working? Here we go. Sketch the function here, and with the goal in mind of putting the new point of tangency over here at 416, because originally we had, we were over here at 2 and we had a tangent line here at 2. So all the stuff in his neighborhood was good. So if you look at it, if we create a new tangent line at the point 4, because if we want to estimate, things in the neighborhood of 4, we can easily do that. So you'll notice that if I do that, then my values are much closer together. So for 4, it'll do a better job than the tangent line at x equals 2, because if you look at x equals 2, the distance from here to here is really great, but if you hang out in that little neighborhood in there, it's not so bad. So if we were to do that, just to show, like let's say we wanted to estimate, 3.9, 3.99, 4.01, 4.1, and so forth in the table. Let's go to the calculator and let the calculator do the calculations for us. So you'll notice that I actually did graph the equation of the tangent line at x equals 4. So you should have something that looks like mine along here. And the nice thing is I can calculate values to do it for us. So if I do second calculate a value, I can go ahead and type in 3.9. And if I hit enter, then if you look at it, my squared is 15.21, and if I press my down arrow, it's 15.2. So if I arrow up again, that's the value, the actual value on the function. This is the tangent line approximation at that point. So it's not even that far off, okay? So, and that's at 3.9. And if I did 3.99, okay, I'm going to do, let me see, 3.99. and press enter. This is the actual value of the function, and if I press my magic down arrow key, it's 15.92. So if I go back up, it's 15.9201 and then 15.92. And by the way, 3.99 is not that close to 4. So what if I actually picked a value that's actually closer to 4, hence 3.999? Excuse me, and that's the beauty of the calculator, is that it can click, oh, I don't know what I just hit there. So it can calculate, let's do this again, a value. Must have hit something else, 3.999, and if I hit enter, I get this, okay? And look at this. Look at how close that is. Are you kidding? It's 0.12345, so that's like 1 over a billionth off from what the actual value is. Are we kidding? So, and that means then that the closer I get, like if I get even closer and closer to 4, then the tangent line and the value of the function are so ridiculously close together that why not use the tangent line? And you guys might say to me, well, why are we using tangent lines? Isn't finding the equation of a line a piece of cake? So why don't we use something that is just so easy to use in our favor? That's how we're kind of looking at it. I'll be right back. I have to use the bathroom. Hi, I'm back, and I'm going back into my workspace. Okay, so if you notice right in front of you, again, we have the same problem. There we go. Okay, so if you look in front of you, well, if you're staring at the computer, you're not really looking in front of you, you're looking at the computer. And by the way, I didn't realize I had that thing still moving when I got up to go to the bathroom. I'm looking at the thing and it was still timing. Anyway, so over here is right now, you'll notice we have a function that we don't know of, but we have a tangent line right over here, and we want to use differentials, which means using the tangent line to approximate f. So the thing of it is we don't know what the function is, but what we can do is find the equation of this tangent line and use it to approximate the function at these particular points at x equals 1.9 and at x equals 2.4. Okay, so here's what we're going to do. The first thing is we figure the point of tangency is right over here, and it's at the point 2, 1. Okay, so that's our point of tangency right now. So we have to find the equation of this line. If you go back to good old precious algebra 1, to find the equation of a line, you would need 2 points. And the beautiful thing is that we do have a point right here that we can use, and this is -1, 0, or we can actually calculate the slope by doing rise over run. That is so old school, but it works, okay? So we're going from here, we are going from -1 up to 1.5, right? So we're going to count. So if we do this, 1, 2, 3, 4, 5. Well, that's actually a half. So that's 1, 2.5 over 2. Hold on. Hold on. I have to go back. Oh my God. Hello. I'm going from here to here. I'm not going all the way up there. I'm going only over to here. I'm losing time as we speak. Dear God. Okay. So from -1 to 1 is 2, right? It's 2, such a dope. 2, and then 2 over this way. So clearly the slope of this line is 1, right? So the slope of the line is 1. So since m is equal to 1, we know the equation of the line is y, -1 equals 1 times x minus 2. So we're going to use this tangent line right here to approximate the value of f of 1.9 and f of 2.04. So we're going to put little approximation symbols for those. So I'm going to hit pause right now to just give myself some time. You guys go calculate them too, and let's see if we come up with the same answer. Okay, so I used the tangent line that I found, right? Again, using old school algebra to determine what the equation of the tangent line was, and now I'm using the equation of the tangent line to approximate the value of these functions because I have no idea what f of x is. So the point of tangency is at the point 2, 1. So after I found that f of 1.9 was approximately 0.9 because, again, it's a tangent line approximation because in here, right in there, that we're looking at in this area right here, 1.9 is really close to 2. So right in there, we're saying that the value of the function is about 0.9. And then at the point 2.04, which is even closer on the other side, is right in here somewhere. And the value of the function is approximately 1.04. Now, before we go any further, the thing of it is here's one thing I want to ask you. Is the approximation of the values of y for this function, is the tangent line approximation an overestimate or an underestimate of what the actual value is? I'm going to make you think about that. And if you want to, pause and then press play again because that's fun. Okay, so if you said because the tangent line is above the curve, right? Because the tangent line is above the curve, that means that the y values on the tangent line function are overestimators of what the actual value is because the tangent line is higher. So the y values on the line are going to be higher than the actual function. If, on the other hand, you have a curve where we're over here somewhere, and then you have a tangent line. That's not really, we'll make a big fat dot there. If we do a tangent line, if the tangent line is actually underneath the curve, then you should all recognize that the values that on the tangent line are underestimations of the actual curve because the y values are actually below because the line is below the curve. So we'll talk further about this, on Wednesday. We still have a quiz tomorrow, and no, this is not on there, but it's good to know this stuff, that we're using tangent lines to beautifully approximate the values of the functions on these curves. And again, if the line is above the function, it's an overestimation. If the line is under, it is an under approximation. I hope you guys have a good day. Take care.